Okay, good afternoon, everyone. Welcome to the last session of our FDP program by today. So, before going into that, please confirm that am I audible to everyone?
Yes, audible.
Okay,
Yes, sir.
okay. Thank you. So, for our today's session, our speaker for the session is Professor Mini Ghosh. So, I would like to speak few words about her work. Professor Mini Ghosh is a leading researcher in the field of mathematical biology at VIT Chennai, that is Vellore Institute of Technology Chennai. Her work focus on the our today's developing session, mathematical models to understand the spread speaker of for the session is Professor including HIV, so TB, and COVID-19. Few words. She also about her work investigates impact Professor Mini environmental factors and lifestyle choices like a leading researcher in the field of mathematical biology at VIT Chennai, PhD from Vellore Institute of Technology Chennai. Completed postdoctoral research at focus on the our today's session mathematical and New Zealand. To understand the spread of for the session is Professor Mini Ghosh, TB, and COVID-19. Few words. She also investigates Professor Mini environmental factors and lifestyle choices like a leading researcher in the field of mathematical biology at VIT Chennai from Vellore Institute of Technology collaborates her work with focus on the today's session and New Zealand. Understand the spread of the session is Professor Mini Ghosh, TB, and several few words. With this background, investigates Professor Mini Ghosh and lifestyle choices like a leading researcher in the field of mathematical biology at VIT Chennai from Vellore Institute of Technology. Analyzing the transition on the dynamic session and session is broadening the
Now, in many talks that what we mean by successful, the successful are the individuals who have infected respectively. So if we are talking about the disease like COVID-19, TB, influenza, etc., everyone is susceptible. And size of this population changes, then we need to consider only adult as children were not susceptible. So like this, we have to understand first. So if we are talking about what mode of transmission, whether it is directly transmitted, everyone is susceptible. That means size of is there or not, or it is being affected like dengue, malaria, etc., Lyme disease, etc. So they are affected. So like this, then homogeneity of population density, whether population is homogeneous or it is mode of transmission, these things also matter. Infection transmissibility of fast infection or it is being to others. Then the immunity level of immunity level of then homogeneity of have witnessed this in the transmission of COVID dynamics. We have seen that also symptomatic and is infection transmissibility. So some who are having good immunity level, they will not show any symptoms. Even though they are infected and they are capable of transmitting disease, but they will not feel sick. So this is also important, but this is not so easy to incorporate on the mathematical model. So recently some papers are coming on this also, so we will explore it. The movement of individuals. If individuals move from one geographic area to another geographic area, then disease also gets transmitted. So this is also important, but this is not so easy. Then infections, incubation time. Okay, the person getting infection and person becoming infected, that is incubation period. The movement of in the case of COVID, we have 3 to 14 days of in this incubation period. This incubation period is long, then also transmission can be more. Okay. Unknowingly, the person gets the disease to others. Then environmental and demographic factors that also play very important. Some environment is like we are considering mosquito-borne disease. Some environment conducive to the growth of transmission and demographic factors that so if population is very dense, if we are talking about India, so more people some small that creates more transmissibility. Some geographic and economic factors that also matter. Economic factors in the sense that if someone delay in consulting doctor, so in that case, he or she can transmit the disease to small others. That is maybe geographic and people for longer duration, and he will transmit the economic factors in the sense that someone delay. So that is also important. If you are well to do and if you are from have some problems in infectious others, immediately one should consider to consult doctor. Infectious period. Infectious period is also important. If infectious period is long, then obviously during that infectious period, individuals transmitting the disease in their neighborhood. Have some. So all these matters, but some of these we can include in our mathematical model. Some is not infectious period. Some are not infectious period. So depending upon that situation, we have to frame the model and try to frame the model which is more close to. So all these matters, but then only we can say some of these model, and also whatever prediction we are getting. That should match with the real life. So, depending upon in every disease modeling, there is a transmission of the disease. So that is through incidence function. So all mainly 2 types of incidence functions are times the susceptibility for the population. So, and what is force of that force of infection here we are saying that is a product of contact rates times the probability of transmission given contact, or then probability that random chosen individual is infected. So product of all these, that is your force of infection, because not all contact lead to transmission. So that is why we have probability of transmission given contact, probability that random chosen individual is infected, and the contact rate. So incidence rate, that is now product of C of n p I upon n times s, so si upon n. Now depending upon contact rate, our transmission will be simple mass action type incidence or standard incidence. So that we are going to see here. So incidence rate, this is called frequency dependent transmission. If contact rate is constant with respect to density, that is C of n is your some constant C naught, then your SI, that incidence term, that will be C naught P SI upon n, and C naught P, if you denote by some new constant say beta, then this will be beta SI upon n. This type of transmission is called frequency dependent transmission or standard incidence or true mass action type incidence. Okay. So this is applicable for the disease which does not depend upon the density of the population. That means if we are talking about HIV, then it is not that if someone is HIV infected, then people in the neighborhood of that individuals will get infected. It is not possible. Okay. So that contact rate, it depends upon that individual's contact. Okay, so that contact will be some constant number. Okay, so he may interact with constant number of individuals. So in that case, to model HIV, we should consider this standard incidence or true mass action type incidence. Okay, so it is not density dependent. Okay, next is density dependence. Okay. So here contact rate is linearly proportional to the population size. So C of n is your Kn. Okay, so in this case what happens that you have that incidence rate that will be Knp Si upon n. And then Nn gets cancelled. You have Kp times Si, and Kp, if you denote by new constant say beta, then we have beta S into I. So this you might have seen this kind of interaction in chemical reaction, simple mass action type incidence. This is called simple mass action type incidence, and you can see here that transmission depends on both S and I. Okay, and it is product of say beta Si. Okay, this transmission is known as mass action or pseudo mass action type incidence. So most of the disease models are based on this kind of this transmission term beta Si. I have seen some models of COVID-19 also where standard incidence is considered, but I feel that that is not appropriate, because if you have influenza or if you have TB or if you have COVID-19, then unknowingly you can transmit the disease to the persons who are seated next to you, or in fact TB infected and transmit the this pathogen to the every individual in any closed hall. Okay, so in that case it depends upon density of the population. So that is why this simple mass action type incidence or pseudo mass action incidence is more suitable to model this COVID-19 or TB or influenza, etc. Okay. So now I am coming to simple SIR model, because COVID models are based on this SIR model only. So I will just discuss just the formulation of this model. So suppose this is a model for measles, okay, where children are prone to this disease. And we assume that total population is constant, disease is self-limiting or curable, disease confers permanent immunity. Okay, and in that case, if disease confers permanent immunity, that means individuals once recover, then that individual will not go back to susceptible compartment again, because immunity is permanent. He will become immune to that disease. Okay, so in that case, the population under consideration, we need to divide into three compartments: susceptible compartment, which consists of individuals who are susceptible to disease, who can incur the disease. Then we have infected compartment I, who are infected and who are capable of transmitting the disease. Then we have recovered compartment, which consists of those individuals who are recovered from that disease. Okay, so individuals moves from one compartment to another compartment, from S to I, and after recovery, they move to R compartment. Okay, so as time changes, the number of individuals in each compartment gets changed. Okay, so we have a rate equation for S, I, and R like this. Okay, so when we are saying ds by dt, that is minus beta Si. Manners is coming into picture because individuals are leaving this compartment and joining I compartment. Okay, so this is the beta Si, is the rate at which individuals are leaving S compartment and going to I compartment. So in I compartment, this is plus beta Si, and once individuals recover, then they move to our compartment. So that is why we have minus nu I here, and individuals are joining our compartment. So dr by dt, rate of change in our compartment, that is nu I. Okay, so this is very simple model where we have sorry. So this is very simple model where we have not considered birth rate, death rate, etc. Okay, natural birth rate, death rate. So if you are going to study something for a shorter span of time, then you can ignore that natural birth and natural death, etc. And here we can see that we have not considered disease-related death rate. Okay, so if we have to consider, I think you can mute others. Okay, so now come to the little bit different model where we have disease-related death rate. So here we have one extra term, that is delta I. So if delta is the disease related death, then this should be in only in I compartment. Okay, so only those who are infected, they can die due to that disease. Okay, so we have minus delta I here. Okay, so this is the modified model including disease related death rate. But if you want to study the things for longer duration, then you must include natural birth and death rate, and that we are including here in the next model, that is this lambda minus beta Si minus mu s. So everything you can see that it's same, except we have this capital lambda here, and natural death rate we have included in each compartment. So natural death rate we need to keep same in each compartment, mu s, mu I, and mu r. Okay. Uh, so this is the improved model where we have considered natural death and natural birth rate. And in general, in disease modeling, we don't do this. We don't solve the differential equation. This is simple model, maybe we can do it, but the thing is this is a very simple model. If we want to include other things, symptomatic compartment, vaccination, etc., then model will be more complicated and there will be more number of variables in the model, so it will not be easy to solve the differential equation, system of differential equation. We just try to see the qualitative behavior of the system. So now come to the another important thing, that is basic reproduction number R naught, which is very important in the disease modeling. So this is nothing but the average number of secondary cases generated by a single case in an entirely susceptible population in his or her whole infectious period. That means when whole population is susceptible and you just put one infected person in that population, how many secondary cases, how many new infected person will be generated from that single primary case? That number is the basic reproduction number. So for a direct person to person transmission, you can compute it very easily, which is nothing but the rate of transmission times the infectious period times the population size. Okay, but for more complicated model, we have a standard method that is called next generation matrix method to compute R naught. Okay. So our control policy should aim to reduce transmission so that R naught can be made less than 1. Okay, since at that level epidemic cannot sustain itself. So what happens that if one infected person is not capable of transmitting the disease to single individuals, then obviously disease has to die out. Okay, so that is the reason that control policies should aim to make R naught less than 1. So if R naught is suppose 1.5, then control policies need to eliminate a fraction of transmission, that is 33% reduction is required, so that R naught can be made less than 1. If R naught is 2, then 50% reduction is required. Now question arises how to achieve this thing. Okay, so this can be achieved by reducing contact, so quarantine, increasing social distances, etc., reducing susceptibility, that is if you vaccinate the population, then obviously it will be less, and reducing infectiousness. If you provide timely treatment, then infectious period can be reduced, and in that way transmission can be controlled. Okay, so the key issues are, everyone knows that if we do this thing it will be beneficial. Okay, but what is the role of mathematical modeling here? So mathematical modeling means who are being targeted, how much effort is needed, and how fast do we need to act. If we want to know the answer of this, then mathematical models, suitable mathematical models can answer this thing. We can get answer through mathematical modeling. Okay. So now question is, why do we care so much about R naught? So R naught is the threshold parameters which determines whether disease will persist in the population or not. R naught determines the initial rate of increase of an epidemic. Okay, it determines the control effort required to achieve eradication. Okay, you will see in my next slide, subsequent slides, that R naught will be in terms of the parameters of the model. Okay, also there are some parameters which one can manipulate, and in that way we can try to reduce the R naught value. Okay, so that is the very, very important, because main aim is to make R naught smaller. Okay, now come to the, because those who are familiar with disease modeling, they might have encountered with backward bifurcation. So I will just discuss little bit about it. So what is backward bifurcation and what is forward bifurcation? So in classical epidemic models, what happens that when R naught is greater than 1, then only disease persists in the population. But in these days, in some cases, for some diseases, we see that even if R naught is less than 1, then also disease persists in the population. Okay, so why it happens, and for what kind of models it happens, that maybe if we think of that, and if I want to discuss, maybe 1 or 2 more lectures will be required, but I will just discuss what do you mean by backward bifurcation. Okay, so what happens in the first graph, you can see that this on x-axis we have R naught, and y-axis we have equilibrium level of infective population. Okay, so as long as R naught is less than 1, we have this disease-free equilibrium point, that is on green line on x-axis. So disease-free equilibrium is stable. when R naught is greater than 1, then only endemic equilibrium comes into picture, and that is stable. Okay. So that is given by a red colored graph. Okay. That curve. Okay. So in the second plot, you see that when R naught is somewhere between 0 to 0.75, you can say we have stable disease-free equilibrium point. But when R naught is somewhere close to 0.75 to 1, in that range we have both green and red colored curve. Okay, so in that case we have both disease free equilibrium point and endemic equilibrium point. Okay, and in this case we get two endemic equilibrium point, and one is stable, one is unstable, and disease free equilibrium also stable. So here I am talking about local stability of the equilibrium points. Okay, so in this scenario, when we can see that from R naught equal to 1, it is going backward and then moving forward. Okay, so this is called backward bifurcation. And if this is the things, then control policies should try to reduce R naught below 7.5. Then only we can say that disease can be eliminated from the population. Because if R naught is somewhere in between 0.75 to 1, then we can't say anything, because we will be having stable disease-free equilibrium point as well as stable endemic equilibrium point. And that means that if we start in the neighborhood of disease-free equilibrium point, system will tend to disease-free equilibrium point. And if we start from the neighborhood of endemic equilibrium point, then system will tend to endemic equilibrium point. So depending upon initial condition, system may go to endemic equilibrium point. Okay, so in that case disease may persist in the population even though R naught is less than 1. Okay, and then come to the type of treatment functions. First one is that linear treatment function. So treatment function is proportional to the number of infectives. So here this proportionality constant is denoted by alpha. So this is the rate at which individuals are recovering and joining to the recovered compartment, or the rate at which they are leaving the infected compartment and moving to hospital care. Okay, depending upon the model, whether you have one more compartment for hospitalized individuals before this R compartment, then you can think of moving these recovered individuals to providing treatment to infected individuals and moving them to hospitals. Okay. Then we have staged treatment function. This was introduced by Wang in 2016. So this says that this treatment function is proportional to number of infectives as long as number of infective is less than some threshold, and that threshold is denoted by I naught. If number of infective is greater than this threshold, then it is a constant, and which is the maximum capacity of the treatment, and that is nothing but I naught. That is the maximum capacity. So when this maximum is reached, then we can't provide treatment to more number of individuals. Okay, so this kind of treatment function is applicable when we have limited resources. Okay, this kind of treatment function we had included in SIS, SIR, and SIS type models. Okay, maybe I just discussed SIR. I will come to SIS. Maybe one model I have included here where we have SIS. Okay, we did it in general without mentioning about the disease, because different disease we model by different types of models, say SIR, SIS, SIRS, etc. So that we had published, and this was with the Chinese collaboration. So now come to saturated treatment function. Okay. So when there is a large outbreak of the disease, infectives are usually delayed for the treatment. Okay, in that case, T of I will not be just Ri, it will be Ri upon 1 plus alpha I. So you can see here when I is very, very small, T of I will be almost equal to Ri, but when I is large, it will be approaching to R upon alpha, that is the maximum capacity. So this is the saturation phenomenon of the treatment, and this function is continuous and differentiable. And when alpha equal to 0, the saturated treatment function reduces to the linear one. Okay. Then we have Hall in type 3 treatment function. This was introduced by Dubey, Dr. Balram Dubey, who is in BITS Plani now. So they considered T of I as beta I square upon 1 plus gamma I square. This corresponds to the situation where the rate of treatment grows very fast initially with the increase in the number of infectives. And then it grows slowly and finally settles down to maximum saturated level. This condition pertains to a known disease which has re-emerged and has available treatment modalities. So maybe for COVID-19 now we can consider this kind of treatment function. In fact, one professor from Satsai Institute, I think he has included this type of treatment function in his model. So this is Hall in type 4 treatment function. This was also discussed in the Dubey paper. So this is T of I equal to beta I upon this thing. This corresponds to the situation where the treatment rate initially grows with growth of infectives and reaches the maximum and then starts decaying. Okay, so it is not staying at one constant value, but it starts decaying. Okay. This can be related with the, if we have limited resource, then we can consider this kind of treatment function. The in spite of high number of infectives, the available treatment becomes very slow because we can't provide treatment to every infected individuals. So this case also may arise when there is re-emergence and a spread of disease in place of limited treatment facilities. Okay, now come to some facts about COVID-19 because I am going to discuss one or two other models on COVID-19. So this is the known fact which I have just taken from World Health Organization website. So COVID-19 is a rapidly spreading viral infectious disease, which was originated from Wuhan in China in December 2019. And it causes mild to moderate respiratory illness. And individuals who are already having cardiovascular disease, diabetes, chronic respiratory disease, cancer, etc., they are more prone to this disease. And if they get infected, then it can cause more serious illness and they may need hospitalization. Okay? The transmission of this disease is primarily through droplets of saliva from nose of an infected person when that person coughs or sneezes. So most of Europe, USA and India are badly affected by COVID-19. And the first case of COVID-19 in India was reported on January 30, 2020. And now it has crossed 44 millions. Okay? So before coming to COVID model, I will just give you this SIS model with this kind of treatment function, and this was published in 2009 with Chinese collaborators. So this you can see that the same T of I is here, and here this is SIS model. Okay. So SIS model generally, SIS model if disease does not give immunity, okay, like we have influenza, etc. So in that case, what happens? After recovery, individuals again become susceptible. Okay, so we should not consider any recovered compartment in this case. So whole population under consideration should be divided only in two compartments, S and I, and individuals move from S to I and then back to S after recovery. So that is why we have this kind of model. You can see this treatment function is here in I. We are providing treatment, individuals are recovering and they are joining this S compartment. And in this case, our R naught, you can see that is beta lambda upon mu, and this thing whole of this. So beta is the rate of transmission, lambda upon mu is the total population size in absence of disease, Okay, when I is not there, total population, S population will go to lambda upon mu. I will be 0, so total population size will be lambda upon mu. So rate of transmission times lambda upon mu, and divided by total period they are spending in I compartment, that is 1 upon mu plus alpha plus gamma plus R, because T of I we are going to write as Ri. So this is your are not. Okay, so this model we had done long back for simple SIS model. So same thing we thought of incorporating for COVID model. Okay, because we read some news that in fact in USA also they are having a problem in providing treatment to every infected individuals. Okay, so, in the case of outbreak of COVID-19, many countries witnessed this thing. They could not provide treatment to every individuals. They had shortage of beds and ventilators, etc. Okay, so that idea only we thought to implement for this COVID-19 model. So in this case, what we are doing is we are going to consider different compartments, and here first is susceptible, then we have exposed individuals, those who are exposed to infection but they are not yet infected. Then we have symptomatically infectious individuals and asymptomatically infectious individuals. Then institutional or home quarantine for asymptomatic people. And then hospitalization we are considering for symptomatic infected individuals. And then we have recovered individuals from COVID-19. In general, we have seen that COVID-19 gives immunity. Means if you are going to consider for shorter span of time, you can see that within 6 months of time or so, individual will not get infected again. But for COVID-19, we have seen that many are infected twice or thrice also. But this for that is a rare case. Okay, so this is our transfer diagram, or you can say estimated diagram of our model. We have S compartment, E compartment, IA, that is infected asymptomatically, then symptomatically infected individual, IS, this is quarantine compartment, and this is your hospitalization thing, that means those who are hospitalized, and we have R for recovered compartment. So individuals are moving from S to E. Then E to some fraction is going to asymptomatically infected compartment. Some are going to symptomatically infected compartment. Then asymptomatically infected individuals may go to home or institutional quarantine center. And if they develop the symptoms, they may join the symptomatically infected compartment. From symptomatically infected compartment, individuals may move to this hospitalized individuals compartment, and after recovery, they may move to R compartment. And there is possibilities of recovery from Q to recovery in Q compartment also. That means individuals, those who are asymptomatically infected, they may move to this R compartment. Okay, and here we have this rate of transmission. Say we have taken different rates of transmission for symptomatically and asymptomatically infected compartment individuals. So we have beta 1 and beta 2, assuming that transmission due to symptomatically infected compartment could be more, because they will be more coughing and sneezing. So beta 2 can be greater than beta 1. It depends, because if you are taking precautionary measure, if you know that you are infected, so symptomatically infected individuals may take precautionary measure and they may isolate themselves, and there could be a reduction in the transmission also. But when there is a outbreak of disease and many are infected, then overall we can assume that transmission due to symptomatic infected individuals could be more. Okay, then we have this factor 1 minus sigma mpm. This is related to the that precautionary measures which susceptible individuals are taking into account. So that is, and the use of face mask and sanitizer, etc., and efficacy of that we are denoting as sigma m. So the rate of transmission can be reduced if you are taking proper precautionary measures. Okay, so that is why we have this factor, and this is lambda. This is the rate of recruitment in the populations, and all individuals who are coming to that region, population under translation, they are going to S compartment due to immigration or birth, etc. That we say rate of recruitment, and natural death rate mu, which is same in all the compartments. Then we have additional death rate in symptomatically infected compartment and also in hospital care, that is mu h and mu s are the additional death rate due to the disease. So keeping this in mind, we have formulated our mathematical model, and you can see here that this is system of uh, 7 8, I think 8 differential equations, and it is not easy to solve this differential equation, but our main aim is to see whether disease free equilibrium point is stable or unstable. We want disease free equilibrium to be unstable, and so disease free equilibrium to be stable and endemic equilibrium to be unstable. Okay, so we try to see the qualitative behavior of the equilibrium point. So we find the equilibrium point first. So for this model, we have also included that treatment function, and which we have included only in symptomatically infected compartments, so T of IS, which is alpha s IS, as long as IS is less than I naught, and which is constant when IS is greater than I naught. So this kind of treatment function is included in that model. uh, and then we computed the equilibrium points like this. Okay, and then we have the basic reproduction number. You can see that basic reproduction number is coming into the model parameters in terms of all model parameters, and some of the parameters we can see that if we want to decrease this, then we need to increase the sigma, mpm, etc. Then obviously this will decrease. If we decrease beta 1, it will decrease. If we increase mu, sigma, alpha, etc., then also this will decrease. But the thing is, some of the parameters we can manipulate, but not all parameters. Natural death rate, mu, etc., we can't change. Okay, it depends upon the country under consideration. Okay, so this is the, when we have say two system of differential equation. One is when is less than I naught, and when is is greater than I naught. So for both the system, we will see what are the equilibrium points. Maybe I will not go in detail. I will just give you what happens when is in between 0 to I naught. So in that case, we see that we have only one endemic equilibrium point when R naught is greater than 1. And in fact, when R naught is less than 1, then also we have only disease free equilibrium point. Okay, but when IS, number of symptomatically infected individuals, that is greater than the I naught, which is the capacity of treatment, in that case, all the equilibrium points you can write in terms of E, its post class, and which is the root of the quadratic equation. Here we are getting quadratic equation, and this quadratic equation may give two positive roots corresponding to this E variable. And once we get two values of E, then we have two equilibrium points, because all other variables can be written in terms of E. Okay, so when is is greater than I naught, then we have possibilities of two positive equilibrium point depending upon the discriminant of the this quadratic equation. Okay, so we can get to positive root if we have this thing. So in that case, we have two positive equilibria, and which suggests that there is a probability of backward bifurcation, and this is exhibited for some set of parameter. So in this situation, where reduction of reproduction number R naught below 1 is not enough for elimination of the disease. Okay, since the existence of backward bifurcation demands a reduction in value of R naught quite lesser than 1 to obtain stability of the DF, disease-free equilibrium point. Okay, so this is the backward bifurcation diagram for this set of parameter, and you can see that you need to be somewhere between 0 to 0.39 or something to have only disease-free equilibrium is stable, or disease-free equilibrium globally is stable. Otherwise, disease-free equilibrium can be locally stable, and in addition to that, we can have endemic equilibrium point also locally stable. Okay, so this we had seen, and this we had done with say I naught. If you increase I naught, there will be certain variation in the exposed population, but increasing I naught beyond certain point will not make any difference. That means capacity of treatment is enough, so no need of no impact of increasing it further. So this is the stability analysis part. So we had found the stability of disease-free equilibrium point and endemic equilibrium point, and we can see that we have some restriction on under some conditions we got this stability of these equilibria. So under some restriction on the parameters. Then this model we did in the beginning of the COVID outbreak. So data we had considered only from February to October for USA, Brazil, and India. And data was taken from this website, and you can see that are not values for these three countries. USA is having 3.5, then India, and then Brazil. And this beta 1, beta 2 also are estimated. And this alpha A, that means rate at which they are moving to hospital, I think. So these parameters we had estimated, and other parameters we have taken like this. And this is just the simple plot. You can see the total confirmed cases of US, India, and Brazil through this bar diagram and pie chart, TB deaths, etc. That simple plots are there. So active COVID cases in India, USA, and Brazil during those periods. Okay, this is the model fitting, and uh, that our model we try to fit to the data, available data, and we based on that we got the estimation of the parameters. And this is the impact of parameters on basic reproduction number. So this is the sensitivity analysis. You can see that we have positive and negative sensitivity indices corresponding to different model parameters. So you can see that mu is having more impact, but we can't manipulate mu even though it is having more impact on the r naught value. Okay, if you increase mu, r naught will decrease. Negative indices means this will have a negative impact. So positive indices means if you increase that parameter, r naught will increase. If negative indices, that means if you increase, then only r naught will decrease. Okay, so we have to see you can see here this lambda, rate of recruitment, that is also very important. Okay, but here a, this is also important. This beta 2, beta 1, this rate of transmission, etc., all are important. So from this diagram we can see that which parameters are the key parameters and which can be manipulated, and based on that we can plan our control strategy. So this is the effect of different parameters on the number of total symptomatic individuals. So we can see that increase or decrease in some parameters will decrease the number of infectives. Okay, this figure is very small, so just this is showing the impact of this sigma m, etc., which is related to that face mask, use of face mask, and use of sanitizers. It means it is associated with the use of this considering the precautionary measures. So from this paper, this work, we concluded that we estimated the transmission rate of disease for symptomatically and asymptomatically individuals, and the rate at which individuals who are quarantined recovered is estimated as well. The estimated parameter implies that disease transmission rate is high in USA, further implying higher infectiousness of the deadly disease. And our study suggests that when infective number surpasses the treatment capacity, then there is a possibility of occurrence of backward evacuation, and which is numerically demonstrated. Okay, so hence in this situation, it is harder to control the disease by just reduce in R naught below 1. Okay. So I will just discuss in brief about one more model only. I will discuss. I think I don't have much time. So this also this work was also done in the beginning, and this is with my PhD scholar now who is doing postdoc abroad, Akhil, and with Chinese collaborators. Okay. So we found that we saw some news that elderly are more affected with COVID-19. So death in elderly people are more compared to the younger people. So keeping this in mind, we tried to frame the model, and we consider data from Italy and Spain. Okay. So we divided the whole population into two groups: elderly individuals and group of younger individuals, and we have this kind of model. Here we did not consider birth rate and death rate because we are thinking of doing this, because if we consider for longer span of time, then young will move to elder people compartment, and then model will be more complicated. So our aim was just to see the things in a shorter span of time. So we just divided a whole population into these compartments. So these are susceptible, exposed, infected, susceptible, exposed, infected for elderly people. Then hospitalized, we combine both young and elderly people. Then we have a recovery compartment. Okay, and we have similar kind of transmission, etc. And we got this mathematical model. You can see here we don't have birth and death rate. And then these are the parameters. I'm not going to discuss these things. So we computed R naught, we computed this equilibrium points, and then we consider the data. Again, this data is for a smaller span of time because it was the start. We had submitted our paper in June, and finally it got accepted in December or so. But the thing is, reviewer didn't point it out that you should update the things, so we left it like that only. So this data we had taken from this worldometer, and we estimated this beta and nu and R naught value for Italy and Spain. We had 2.6 and 2 point like this, and this is the curve fitting plot. Uh, Okay, and this we then extended that model for optimal control problem, and we included this optimal control parameter here, UN, which is related to reduction in the transmission, okay, due to control measures, to precautionary measures. So beta can be reduced here. So this UN is UN of t, and so 1 minus u1 times this u1 can be 0 to 1. If u1 is very very high, then this transmission can be reduced means dramatically. Then we have here one more parameter, that is that optimal control parameter, that is u2, the rate at which their infectives are moving to H compartment. Okay, so u2 here and u2 here. So from I1 and I2, movement of individuals from I1 and I2 to hospital, that is timely, providing timely treatment, that is also important. So here u2 of t, that is also optimal control parameter. And we found that uh, optimal control model gives better result. So maybe in 120 days, if we see the number of infected cases with and without optimal control, so with control, this red curve you can see that is less than that blue curve, so it is going down. Okay, so optimal control is effective. So I am not going to discuss more on this. Those who are interested can go through my research papers, our research papers. In fact, all these work, whatever we have done, that research scholars contribution is more, I am just guiding them. So you can read the full paper, and if you have any query, you can always ask me. Okay. So these are the issues and challenges to tackle the spread of COVID-19 in India. In fact, now it is under control, but we don't know because different strains are there. So if new strains are coming, and if vaccination, whatever we have, that is not effective, then again situation can be beyond our control. So keeping this in mind, I am just saying that population size is very large and not everyone is following the guidelines by government. Incubation period also varies. Number of asymptomatic cases are more in our country. we are having more young people. So maybe that immunity level of young people will be more. So in that case, they will not show the symptoms. So we can have more number of asymptomatic cases. There are areas where it is not possible to maintain social distancing. Then home quarantine is also not feasible because some where some people, maybe in one house there are 10 or 20 people, so it is not possible to isolate the infected individuals. And testing and screening also started little late in our country, and in the beginning people didn't take it seriously. And our medical facilities are not sufficient to cater huge population. If there is again some outbreak of this disease with different strain, then we may face problem again. Okay, so this work uh, we did, we got grant from DST, and that was a special grant on COVID-19. So I must thanks DST SCRB for providing me this grant, and thank you all. If you have any question, you can ask.
Okay. Thank you, Professor Mini Ghosh. Thank you, ma'am, for the insightful presentation. Is there any question regarding the talk? Please ask.
Hello.
Yes, yes.
Hello, ma'am. You can suggest any book, ma'am, for this topic?
Mathematical biology, mathematical modeling of infectious disease. I think J.D. Murray book is there. That is the basic book. Okay. After that, many new books are there. So maybe you can write me. I will send you the some link for soft copy of the related book. But J.D. Murray book, that is the basic book. It has 2 volumes. Okay. So that you can refer. And Fred Brewer and maybe a few Chinese authors, they also published some books on this mathematical biology. So I will give you the reference. Okay.
Okay, thank you, ma'am. How can solve this type of problems, ma'am? Uh,
Actually, we
how we
don't
can solve
solve
this
it.
type of
We
method?
don't solve it numerically. Only we solve it. We use different software, like I use MATLAB or XPP. Mathematica also you can use. When I was doing my postdoc, that time I had used Mathematica, but after coming back to India, I didn't use Mathematica. R also you can use to solve the this system numerically. Also to do some that curve fitting, etc. You can use R also there. Okay, in MATLAB we have matcont also, matcont that gives you the bifurcation diagram, etc. So that you can run using MATLAB. From MATLAB platform also you can run matcont. Okay, and that gives you the bifurcation diagram for different one parameter bifurcation, 2 parameter bifurcation, etc.
Thank you, ma'am. Thank you, ma'am.
Yeah.
Any queries? Any question regarding the talk?
Hello.
Yes.
Hello, ma'am. We can compare the study for the diseases, ma'am. Like
Comparative study.
dengue,
Please elaborate it.
malaria, chikungunya.
Aha, you can do, but the different disease will have different things. Means some disease you need to model using SIRS type model. Some disease you should model using SIR type only. So based on our disease only, you are formulating the model. Okay, you can compare the disease dynamics in different population and in different time frame.
Yes, ma'am.
Okay. But comparing different disease, that may not be possible, because you may consider SIR model for COVID-19 and SIS model for influenza. But even if you are considering mosquito-borne disease, you can see that malaria, that is of SIS type. But dengue generally it gives immunity. Okay. So for dengue, you need to consider SIR type model, but for malaria, you need to consider SIS type model. Okay, so again, you can't compare these two diseases, but certainly you can consider the disease dynamics for a different geographic region and a different time frame.
Okay.
Okay, any question? Any further question?
Any questions? Okay. I am assuming there is no queries so far. So we will wrap the session here. Thank you, ma'am.
Yeah, yeah. Thank you very much.
Thank you,
Thanks to
Professor.
all for
Thank you.
your careful listening. Yeah.
The feedback link will be shared in shortly in the WhatsApp group. Okay. Thank you, ma'am. Thank you, everyone.
Yeah, yeah. Thank you all.